Assalamualaikum, my name is Siti Rukaya. Firstly, we go through introduction. As we know, Hplc uses a liquid mobile phase to separate mixed component by dissolving analytes in a solvent and pushing them through a column under high pressure. Hplc also can separate a wide range of chemical mixture, including non-volatile and thermally unstable compound. Example list include organic, inorganic, biological sample, synthetic or natural polymer, and thermally labile compound. Hplc, or we known as high performance liquid chromatography of application, is about any compound with solubility in a liquid that can be used as mobile phase. Its application range from analytical to preparative purpose, including the analysis of sugar, pesticide, residues, organic acid, lipids, amino acid, toxins, and vitamin. The advantage of Hplc include its a greater sensitivity enabled by various detectors, reusability of column for multiple analysis, suitability for both ionic species and large molecule, and efficient sample recovery using fraction collector. We move to the objective of this analysis. First is determine the retention time of a standard caffeine solution. Second, identify the caffeine peak in
a tea and coffee sample.
The last one is to determine the amount of caffeine
in a tea and coffee sample
using a response factor method.
Hi and Assalamualaikum. My name is Nur Natasha, and what I will present about my part which is methodology of block diagram of Hplc. The caffeine standard and sample we will be going through. Firstly, the solvent reservoir. Mobile phase contain a container in a glass reservoir, and then the mobile phase or solvent in Hplc is usually a mixture of polar and non-polar liquid component whose respective concentration are depending on the composition of the sample. And then next, for the part it aspired the mobile phase from the solvent reservoir and force it through the system column and detect depending on several factors including column dimension, the particle size of the stationary phase, the flow rate, and composition of the mobile phase. Operating pressure of up to 42,000 kilopascal can be generated. And then next, for the sample injector, this injector can be a single injection or even an automated injection system. An injector for Hplc system should provide an injection of the liquid sample within the range of 0.1 until 100 ml of volume with high producibility and under high pressure. And then for the column are usually made of polished stainless steel and are between 50 and 300 ml. Next, I will be moved to the Hplc setting. To accurately determine the caffeine content in tea and coffee, we use an optimized Hplc method. Here is an overview of the system and the key parameters. Firstly, Hplc instrumentation. We use a Shimazu model 1514 Hplc system. The separation of performed on a Zorba Eclipse Plus C18 column with a 5-part size, 4.6 mm internal diameter, and 150 mm length. Secondly, mobile phase and flow parameter. The mobile phase consisted of water and methanol in a 16:14 ratio. Both solvents were of Hplc grade to ensure precision. The flow rate was set to 1 ml per min for optimal separation. This solvent ratio and flow rate are suitable for caffeine separation because the methanol is a good organic solvent for caffeine polarity. Thirdly, detection condition. The column was maintained at 40 Celsius to stabilize the spiration process. Detection was performed using a UV detector set at 275 nm, which is the absorption maximum for caffeine. Lastly, sample injection. A 10 sample was injected into the system for analysis. This volume ensures consistency across tire.
Hello, my name is Noizati binti Hassan Basri, and I'll be explaining to you about my study based on result of caffeine analysis using high performance liquid chromatography, which is also known as Hplc. Let's begin with the calibration curve in figure 1. It demonstrates the linear relationship between caffeine concentration and peak area with an equation of y equals to 25,008 px minus 1,745.3 and a strong R value of 0.9928. This high linearity ensures accurate quantification across a range of concentrations. Next, figure 2 shows that chromatogram of caffeine at 2 ppm. The sharp symmetrical peak at a retention time of 2.6 minutes confirm that the caffeine is well separated under these conditions. Figure 3 displays the chromatogram of a tea sample, analyzed under the same conditions. The retention time matches that of the standard, confirming the presence of caffeine. The peak area was used to determine its concentration by comparing it to the calibration curve. Additional peaks may represent other compounds in the tea. Table 1 and 2 highlight the method's precision. Intraday repeatability results show minimal variability with an RSD of 1.14%, while interday repeatability had an RSD of 1.46%. Both are well below 2%, indicating excellent precision and reproducibility for this analysis. Table 3 shows the recovery of caffeine. Values range from 97.6% to 98.4%, demonstrate the method's high accuracy and suitability for real sample analysis without significant loss or interference. Finally, Table 4 provides the caffeine content in tea and coffee samples. CTC teas had the highest caffeine levels, range between 2.49% and 3.44%, while roasted coffee beans and powders had slightly lower levels. Green tea, known for its milder caffeine content, ranged from 2.3% to 3.4%. In summary, this study demonstrates that Hplc is a precise, accurate, and reliable method for analyzing caffeine in diverse samples. It provides valuable insights for quality control and consumer choice.
Hi, my name is Natasha and I'm going to discuss about this experiment. In this experiment, the Hplc method was highly effective at separating caffeine from other compounds with minimal interference. Caffeine was identified at a retention time of around 2.66 minutes. The calibration curve shows strong linearity with an R2 value of 0.9928, ensuring accurate and reliable quantification. The method was also very sensitive with a detection limit of 0.2 ppm and a quantification limit of 0.7 ppm. The caffeine level we measure in tea and coffee sample range from 2.5 until 3.53% for tea, and the other for coffee is 1.17 to 1.34% based on dry weight. Variation we observe could be due to factors like regional difference or how the sample were prepared. Overall, the method proved to be reliable with precision results showing less than 2% relative standard deviation, with highlight its reproducibility. This makes the Hplc method ideal for routine quality control of caffeine-containing products. Ensure that they meet safety standards such as keeping caffeine level below 200 ppm. That said, there are some areas for improvement. Minor issues like baseline noise and overlapping peak could affect accuracy slightly. This could be addressed by using techniques like gradient illusion, or more advanced sample preparation to further enhance the method performance. In conclusion, this validated method is both reliable and efficient for analyzing caffeine in tea, coffee, and similar beverages. That's all.
We move to the conclusion. In this experiment, we successfully determined the retention time for a standard solution of caffeine, which was found to be 2.482 minutes. This value serves as a benchmark for identifying caffeine in other samples. For the soft drink samples was analyzed, we identified the caffeine peak areas as follows. Sample 1, the caffeine peak area was 57.3551%. Sample 2, peak area was determined to be 55.3200%, and sample 3, 100,000%. This result highlights the variability in caffeine content across different soft drink samples. This variability can result from difference in formulation or caffeine concentration among the samples. Overall, the experiment demonstrates the utility of Hplc in quantifying caffeine content and distinguishing the retention time of caffeine in complex mixture, like soft drinks. This analysis is crucial for ensuring product consistency and adherence to regulatory standards. We move to the application of Hplc in food analysis. High-performance liquid chromatography (HPLC) is a key tool in food analysis, known for its precision and adaptability in detecting and quantifying various food components. It is widely used to measure nutrient levels, detect contaminants, and analyze additives in food and beverage. HPLC ability to separate and identify complex mixture makes it ideal for ensuring food safety and quality. It can detect trace contaminants like peptide or mycotoxin, verify authenticity, and analyze nutrients such as vitamin or caffeine with high accuracy. This technology is vital for regulatory compliance and maintaining consumer trust by ensuring transparency, safety, and consistent quality in food products. Its versatility and reliability make HPLC a cornerstone in modern food science.